Tern sequence, a famous Göttingen mathematician from the 19th century. Here is his sequence. It can be described in several ways. It's very important. It's one of the bigger entries in the OEIS. But let me give you the simplest definition. The first two terms are 1 and 1. The next two terms, I copy the 1 and the 1 and put their sum in the middle. So the sequence now begins 1, 1, 1, 2, 1. And how does it continue? I copy the previous line, and in between, I put the sum. 1 plus 2 is 3. 1 plus 2 is 3. So I've now shown you
sort of Pascal triangle.
It's very like Pascal. It's actually like Fairy series, F-A-R-E-Y. If you know, it's a very common number theoretic thing. So again, to get the next 7 terms, I copy the previous line, and in between them, I write the sum of the 2 terms above it, just as you said, just like Pascal's triangle. Now this has a very nice property. If I omit the last one, it has the property that if you look at ratios of successive terms, fractions, 1 over 1, 1 over 2, 2 over 1, 1 over 3, a third in short, 3 over 2, it's 1.5, 2 over 3. If we keep doing that, we get all the fractions in their lowest terms. It's a way of enumerating the fractions. After a while, we get 7/17ths, we get 101 over 103, and so on. We get 103 over 7. We get all of them, little ones and big ones, and they're always reduced. So that's the sequence. 1, 1, 2, 1, 3, 2, 3. Just read it like you do with Pascal's triangle. If you plot it, you get something that looks pretty nice, like Monet sketching the facades of some cathedrals. This is Hofstadter's Q sequence, and the interesting thing is that we don't know if this exists or not. It's an open question, just as we don't know if Schrödinger's cat is alive or dead. Fibonacci says that A of n is equal to A of n minus 1 plus A of n minus 2, sum of the 2 previous terms. Hofstadter sequences, A of n is A of n minus A of n minus 1 plus A of n minus A of n minus 2.
Can you show me an example how that works?
Well, I guess.
All right.
All right, I'll try. It begins with 2 1s, just like the standard naive Fibonacci version. We don't put a 0 in here. You go back 1 step and you go back 2 steps, right? That's how you get Fibonacci. You look at where you are, you go back 1 step and back 2 steps and add them up. This one, Hofstadter's Q sequence, you look at the previous term, but that's how many terms you have to go back to get the thing you're adding. So what's 3? So going back 1 step gives us a 1. Going back 1 step, because of that 1, gives us a 1. 1 plus 1 is 2. So 4. And what's A of 4? We look at this 2. So we go back 2 steps. 2 steps, we get a 1. We go 2 steps back and we get a 1. And that says go back 1 step and we get a 2. 1 plus 2 is 3.
So that one... So that one told us go back 1 step, but 1 step from our starting point again.
Yeah, and whatever you see under your finger, you add it to the other one.
Let me see if I can get the next one. Let me see if I can get it. So for the 5th term, that's a 3. So go back 3 steps.
Yes.
1, 2, 3. So a little 1.
Okay.
So then we go back 2 numbers, which says...
Go back 2 numbers to there, and what do we see? We see a 2. So we add that to the other number, so we get a 3.
Let me see if I can get the next one right then.
All right.
So the 6th number.
Yeah, 6 term.
3. So
3
go
back.
1, 2, 3. So give us a 2. 2, and now 3. So go back 3 steps.
All right.
1, 2, 3. A 2.
Again.
So it's a 4.
Yeah.
And once more to make sure I've got it. So 4 steps. 1, 2, 3. A 2.
2.
And 3 steps. 1, 2, 3. A 3. So that's a 5.
Very good.
Okay.
That's the sequence.
Wow,
now, if we're lucky, we can always do that. But suppose there was a number here which was too big. And that would say, oh, you've got to go all the way back here, where it's not defined. If that happens, you're dead. It hasn't happened yet, but we can't prove that it never happens. Pretty obviously is never going to happen if you look at the graph. This is 10,000 terms. So most of the terms are half of n. We'd run into trouble if we had a term that was as big as n. because this line has slope 1/2, and even though there are some little dots trying to escape, some little particles trying to get away, they have to get it all the way up to here or something before they would kill it. And it hasn't happened, and it's not going to happen. We've checked. Roman Pierce computed 10 to the 10th terms. Never a problem.
But not proven.
Not proven. Here's a picture of 100 million terms that I got from Douglas Hofstadter, who invented the sequence. And you can see beautiful ribbon-like structure, but no proof. It could die at any moment. Beautiful.
You got another one.
And it's a variant, slightly different rule, but an even more striking picture. Look at this ribbon-like thing. This one we know exists. It's just a beautiful picture, a beautiful graph.
What's the sequence that's a graph of?
It's called a chaotic cousin. It's like the other one, but different. And I'm not going to show you the equation because it's an equation and you hate equations. But it's similar.
Okay.
Okay, I mean, it looks like that. That's the definition. This is a sequence that was invented by Remy Secrest. It's a very simple rule, but a little subtle. You've got to put down a non-negative number, and always the smallest possible. So don't put a 0. No one is going to object to that. Now, 1 and 2, if you look at them in binary, 1 looks like 1 and 2 looks like 1, 0. And you notice there's no place where they both have a 1. 1 in binary and 2 in binary have disjoint sets of 1s. They don't overlap a 1. So there's no constraint. As long as they don't overlap, you can have the same number. Okay, now 3. 3, 1, 1 in binary, and that overlaps both of these two. So I can't put a 0 here, because we'd have two numbers whose binary representations met that had the same number. All right, so it's a 1. Now 4. 4 is pretty good, because it's not going to overlap with anything. So I can put a 0. 5, 1, 0, 1. Now I have to be careful. I can't put a 0 here, because it would overlap with that. And I can't put a 1, because 3 and 5 overlap the lowest order bit. So I can't put a 1, but I can put a 2. 6 is 1, 1, 0. What can I put here? I can't put a 0 because of the 2. I can't put a 1. I can't put a 2 because 5 and 6 overlap. So I have to put a 3. And that's it. That's the sequence. And what does it look like? It looks like the Alps on a snowy day.
Right. That's
it.
That's a strange one, that one.
Yeah.
Thank you for watching. Also, a very special thanks to our Patreon supporters. Just some of them are the names you're seeing on the screen at the moment, and you can join them by going to patreon.com/Numberphile. This was the third and final in our trilogy of amazing graphs, at least for now, until Neil shows us some more. If you'd like to watch them all, there are links on the screen and in the video description. And we'll be back again soon with more Numberphile videos.
You're probably wondering what Fibonacci looks like.
I was, yes, right from the start.
Here it is, it's boring. This is the first 200 terms, and they go along and, they get pretty big. When we do these plots in the OAS, the first plot is 200 terms,